In this video, we discuss lesson 1.3, learning outcome number 5, which is about confounding and 4 types of experimental designs that will allow us to minimize confounding. So here's an example. This is a really poorly designed experiment. Suppose you're looking at the effects of aspirin on heart disease or heart conditions, and you put all of the women in the treatment group and all of the men in the placebo group. And then you give all the women aspirin and you give all the men placebos, and then you say, well, did the aspirin help or not? Can you think of what would be wrong with this design? I hope you said, well, we would not be able to tell whether the aspirin caused the result or the fact that they were women caused the result. When we align this treatment group with this group of women, now we are no longer able to tell why the results are what they are. So let's say that everyone in the treatment group got better. Well, maybe everyone in the treatment group got better because they used aspirin, or maybe everyone in the treatment group got better because they were women. And it's really impossible to tell. And that's called confounding. Confounding is when the experimenter is not able to distinguish between the effects of different factors. And our goal is to try to plan an experiment so that this does not happen. There are 4 types of experimental designs that we'll discuss in this course that will allow us to do that. Here's the first one. We've got a completely randomized experimental design. So basically what you do is you look at all the possible subjects and you randomly select them and you put them in the treatment group, and you randomly select people to go in the placebo group. Everyone's assigned through random selection. That's going to be much better than treating all the women and not treating the men, or treating all the men and not treating the women. We don't want that lack of clarity between whether or not that treatment is actually having the intended effect. So this will control for that lack of clarity, for that confounding. Another possibility is to separate all of the subjects into what are called blocks. This is called randomized block design. A block is a group of subjects that are similar, but blocks differ in ways that might affect the outcome of the experiment. So if we're talking about the effect of aspirin on heart conditions, well, aspirin might affect women and their heart health differently than it affects men and their heart health. So it might be important to separate men and women when we look at our data. So one way we can do that is we can first separate everyone into blocks. So you form a block of people that have one quality that may affect the results of your study, and then you form a block of people that have other qualities, and so on. You go on through all the blocks, and in our example, we've got a block of men and a block of women, and then from each block, you randomly select subjects to be treated. So we randomly select some women to be treated, and we randomly select some men to be treated, and then everyone else gets the placebo. And this way we would be able to tell whether the treatment was the cause of the certain outcome, if treating people with aspirin in general actually helped their heart health. But we'd also be able to look at the size of the effect on women and the size of the effect of the aspirin on men, if those were statistically significant. So separating everyone into blocks like this will actually give us more information. And if the effect on women and the effect on men are different, we'd actually be able to see that in the data if we used a randomized block design. So this is an excellent design for controlling the effects of variables. Another design for controlling the effects of variables is called matched pairs design. So one example of a matched pairs design is where you look at the same person, the same subject, and you look at them before treatment and after a treatment. So maybe we've got Jill here, and we want to know if some training actually helps Jill. So maybe you give her a before quiz, then you have her go through the training, and then you give her an after quiz. So it's really important in that case that Jill's before score goes with Jill's after score. So that's a matched pairs design. So we still have sort of a placebo group and a treatment group, but the treatment group is the after group. Another example of a matched pairs design would be a twin study. We would want to pair those twins up and have one twin receive the treatment and one twin not receive the treatment, and then see if the treatment affected affected those who were treated differently, or how that treatment affected those who were treated as compared to the twin that didn't receive the treatment. So it's very important in that case that the pairs are matched up as well. We wouldn't want to have two sets of twins and then like pair their data, pair datas of twin, or the data of two twins from different families. Like that really wouldn't make any sense. So what we do is we compare the treatment groups by using subjects matched in pairs that are somehow related or have similar characteristics. And that's like a twin study or a before and after type arrangement like this. Another type of design is called a rigorously controlled design. It's actually very similar to that matched pairs. And it's one in which we carefully assign subjects to different treatment groups so that those given each treatment are similar in ways that are important to the experiment. This actually is kind of like matched pairs, but we're not looking at the same person before or after. We're not looking at a twin in the treatment group and their twin in the placebo group or non-treatment group, or the one that's receiving the placebo. Instead, we are finding people that have certain characteristics or finding subjects that have certain characteristics and making sure that there is a person with similar characteristics in the other group. So this was an example in an older edition of this text, or this is my modification or my memory of an example in an older edition of this text. Here's this young man. Let's say you've got a late 20s Caucasian male smoker who's a philosophy major, and you put him in the treatment group. Well, if the fact that he is in his late 20s, the fact that he's Caucasian, the fact that he's male, the fact that he's a smoker and a philosophy major might affect his response to some treatment. Well, if you've got all of those qualities in him, you might want someone with very similar qualities or identical qualities in the placebo group. So if you've got two late 20s Caucasian male smokers that are philosophy majors, you put one in the treatment group and one in the placebo group. And this is a rigorously controlled design, which is actually very difficult to pull off. So let's summarize those 4 designs. We've got the completely randomized experimental design, in which subjects are randomly assigned to treatment and placebo groups. Then you've got the randomized block design. So you separate the subjects into blocks that might be important to the outcome of the study, and then you randomly select people within each block to receive the treatment. You've got the matched pairs design, just something like a twin study. It's before, or looking at someone's data before and after some treatment. So that will control for all the differences between individuals in the study. And then you've got rigorously controlled design, which is rigorously controlled because you find people that have identical characteristics, or at least characteristics that are identical, or people that have characteristics that are identical, that are important to the effect of the supposed effect or the intended effect or the expected, I guess, effect of the treatment. And you put them into the different treatment groups or the treatment and placebo group. So all of these can address what's called confounding. Again, that's the inability to distinguish between the effects of different factors. So if we're dealing with the same person before and after, we're controlling lots of variables, because we had the same person at the beginning that we had at the end. The only thing that changed for someone in a matched pairs design was the treatment. Or when you talk about a twin study, well, those are two individuals who are biologically similar, very similar. And the major difference between them would be the treatment, especially if they were raised in the same environment, twins that were raised together. The randomized block design will allow us to sort of tease out the effect of each of the characteristics that define those blocks and how that might affect the sort of overall measure of the effectiveness of some treatment, and how the treatment affects individuals within each particular block. So you've got some more data that you can analyze there, and you might be able to come up with better, more meaningful conclusions. And then, of course, completely randomized experimental design, just randomly putting people into groups, actually is surprisingly effective at creating similar groups and allowing us to focus on just the treatment itself. And so all of these help us to address confounding.